Section 5.1 is on page 268, talks about eigenvalues and eigenvectors, an idea that we're going to use for the next 3 sections. And we're going to use it in differential equations as well when we go back after this. So an eigenvector of an n by n matrix, a square matrix, is a non-zero vector such that ax equal lambda x. Well, obviously, if you let x equal 0, those are equal. For some scalar lambda, a scalar lambda is called the eigenvalue. So you got to remember that. Eigenvalue is lambda. And x is the eigenvector. And of a, and there is a non-trivial solution of x such that ax, such x is called the eigenvector to the corresponding lambda. Now, solving ax equal lambda x in actual applications turn out to be a lot of work. So instead, we say if you have ax equal lambda x, that's the same thing as saying ax minus lambda x equals 0. And that is the same thing as saying a minus lambda in matrix land. 1 is really the identity matrix equals 0. And since x cannot be 0, you're not interested in the trivial case, it must be that a minus lambda I equals 0. So, if you can solve a minus lambda I equals 0, that equation, come up with the lambda, that will be perfect. Now, in the beginning, they're going to give us the question and the answer, and it's just plugging things in, really. So they're asking, is lambda equals negative 2 an eigenvalue of this? Well, let's see. What does that mean? Again, we just learned about this. Let's go by definition. It states ax equal lambda x. So they're asking, is lambda equal negative 2 an eigenvalue of this? Or a minus lambda I equals 0 has a solution? Well, if I take a, that's given. So one way of doing this is for me to figure out, well, a minus lambda I equal 0, 0. Right? Normally we don't write this, but I'll show you how that goes. No big deal. This means what? That would be, and I'm going to write them out, 7, 3, 3, negative 1, plus 2, 0, 0, 2. Right? We're trying to see if we could get that to be what? 7, 9, 3, 3, 1 equals 0, 0. Isn't that like an augmented matrix? And if I take negative 3 row 1, add that to row 2, put the result in row 2, what do I get? So doesn't that mean that x2 is free? Awesome. And doesn't that mean that 9x1 equal negative 3x2 or x1 equal negative x2 over 3? So wouldn't we say the solution is x is x2 times negative, oops, not 3, 1/3, 1? Or simply they would say 3, negative 1 will do. Any multiple of that will do. So they're asking, is lambda equal -2 an eigen? Yes, it is, because I was able to get a solution. The only time that wouldn't work if I really get no solution. To demonstrate this differently, you could have also said, does ax equal lambda x? Would a x equal lambda x? Again, just to show you how this works. Wouldn't that mean 7x1 plus 3x2? This is 2 by 2. This is 2 by 1. The outcome is 2 by 1. And 3x1 minus x2 equals -2x1, -2x2, right? And wouldn't that mean that you are really checking at with 7x1 plus 3x2 equal -2x2, and with 3x1 minus x2 equal -2x2. Have we seen that? Because two matrices are equal if and only if the integers are equal. And isn't this really saying 9x1 plus 3x2 equals 0? And 3x1 plus x2 equals 0? And do we see that that's really what we got? So instead of doing the traditional ax equal lambda x, which is a lot of work, it's much easier to solve just this. And we don't even put the 0, 0 at the end because you can never change them. We assume they're there as we're doing work. So normally, when we write those, we simply write 9331. We do row reduction because we know it equals 0, 0. There's nothing you could do by matrix operation to change those to anything other than a 0, because you could multiply a row by a number and add it to 0. That's going to be 0. So in the beginning, it's a bit confusing because you're not sure what they're asking for, and you can use the definition only in the first couple of problems. They're asking, is this vector an eigen? Is this an eigenvector of this matrix? If so, what's the eigenvalue? Does ax equal lambda x? Well, what's ax? Ax is 367,337,565 multiplied by 1, -2, 1. Does that equal some multiple of 1, -2, 1? Hey, isn't that 3 by 3 and that's 3 by 1? Isn't the outcome of 3 by 1? Doesn't this mean that this product right here is going to be what? It's going to be 3 by 1. And that's going to be the multiplication. Remember how that goes? Take this multiplied by this. 3 minus 12 plus 7. 3 minus 6 plus 7. And 5 minus 12 plus 5. So the left side, we're still checking if that equal lambda times 1, -2, 1. Isn't that 10? That's a -2. That is a 10, a -4, and a 10 minus 12, -2. Can you think of a number that you multiply 1, -2, 1 with to get that matrix? Well, yeah. If you let lambda equal... Oh, the signs are not matching. Oh, that's a positive. Perfect. Yeah, otherwise I was going to say no. Can't you take -2, multiply this by a -2, multiply this by a -2, and multiply this by a -2? So yeah, it works. So yes, there's the eigen value right there for the eigenvector 1, negative 2, 1. Kind of like the way we figured out the negative 1, 3. Except here it's a 3 by 3. Now what? Is lambda equal 3 an eigenvalue of this matrix? If so, find one corresponding eigenvector. Well, what are we going to do here? We're going to do the same thing. We're going to say, well, let's see. Does AX equal lambda X? Right? Well, what's A? 1, 2, 2, 3, negative 2, 1, 0, 1, 1. Multiplied by this X vector, right? And does that equal lambda is 3, 3x1. I just showed you that on the first example. Or I could say, let's take A minus lambda I. It turns out that's really the key. Set it equal to 0 and solve. Well, A is right there. Minus lambda times lambda times I. Well, I is 1, 0, 0, 0, 0, right? If you multiply by 3, that's 3, 0, 0, 0, 3, 0, and 0, 0, 3. Remember, I'm setting this equal to 0, but I'm not going to write that down like I said. I'm just going to find this matrix, reduce it. You could make it augmented and set it equal to 0 and solve. Wouldn't that be 4, 2, 2? I'm sorry, not 4, because you're subtracting, minus. Wouldn't that be 3, negative 2, 2, 2? 3, negative 5, 0, and 0, 1, 1 minus 3 is a negative 2. And if I want to use row reduction on it, if I do the magic, I'll get 1, 0, negative 3, 0, 1, negative 2, 0, 0, 0. This has a solution. Actually, it has an infinite solutions. And now what? Now, wouldn't you say, I'm going to take x3 will be free. Again, if you're not sure. x2 will equal 2x3. And x1 will equal 3x3. So isn't it x3 times a multiple of 3, 2, 1 will do? Or any multiple of 3, 2, 1 will do. Right? So we say, this is the eigenvector, which is what they want, right? Or any multiple will do. Oops, couple of things. Okay, do we know what they're asking? 9 through 16. It says find a basis. Well, what's the deal with this basis business? Basis is a big deal. And let's see how that works. It says the eigenvalues of a triangular matrix. Remember triangular? Are the entries on its main diagonal. The eigenvalues. If you have a triangular matrix, the eigenvalues are the entries on the diagonal. If you get upper or lower, it doesn't matter. As long as one of those is triangular, those are the eigenvalues. If v1 through v sub r are eigenvectors that correspond to lambda 1, lambda n, distinct, meaning non-repeated, for an n by n matrix, then this set right here, these eigenvectors are linearly independent. And what's the deal with bases? when it says find a basis for the eigenspace corresponding to the listed eigenvalue, they're saying find the linearly independent eigenvectors. And how do you do that? Well, we could start with, we want ax to equal lambda x, or simply we want a minus lambda I times x to equal 0. And how does that work? A minus lambda I, 10, negative 9, 4, negative 2, minus lambda, lambda is a 4, times I, 1, 0, 0, 1. And that's going to be 10 minus 4, a 6. Negative 9 minus, that's a negative 9. 4, that's a 4. So the only terms that get affected are those two. And negative 2 minus 4 is a negative 6, right? So we're trying to solve that. And if we reduce this, that turns out to be 1, negative 9 over 6, actually here. If I divide the top by a 3, that's 2, negative 3. And if I divide the bottom by a 2, and it's very simple now to see that if you take negative row 1 plus row 2 and row 2, remember, I'm not putting that right there. I'm putting the 0, 0 on the right of the augmented matrix, but that's the assumption. Well, that means what? That means x2 is 3 and 2x1, so x1 is 3x2 divided by 2. What that means, any multiple of, if I call this 1, this is 3 halves, they don't like that. They always make that an integer. So they say 2, 3. I'm sorry, 3, 2. 3, 2. So they say find the basis for the eigenspace. Well, a basis for the eigenspace corresponding to 4 is the 3, 2. No, I don't know why I put that there. I have plenty of room. So each corresponding eigenvalue will yield an eigenvector. If you notice this is 2 by 2, you can get at most 2 eigenvalues for this, which means you could find 2 corresponding eigenvectors, and those are extremely important. I have 2 more examples to go. So again, busy work, nothing more. If I look at number 12 and I want to proceed, they gave me 2 eigenvalues. If I take lambda equal 1, I want to find the corresponding eigenvector with that. That's going to be the determinant of a minus lambda I equaling to 0. That is, if I really do this, a minus lambda I is going to be 7, 4, negative 3, negative 1, minus 1, 0, 0, 1. What would that be? That would be 6, 4, negative 3, negative 2. If I take twice row 2 plus row 1 in row 2, I will zero this out. This indicates that, again, x2 is 3, and x1 is 2 over 3x2. So the corresponding eigenvector, again, they don't like fractions, so they multiply by 3, right? They say instead of 1 here and 2/3 there, they will say 2, 3. That corresponds to lambda equal 1. And you do it again for lambda equal 5. Again, you would take a minus lambda I, and that would be 7 minus 5 is a 2, 0, negative 3 minus 1 minus 5 is a negative 6. And let me think really quick. 7 minus 5 is a 2. And, oh. Seven minus 5 is a 2 and a 4 and a negative 3, and negative 1 minus 5 is a negative 6. Yeah, that's true. And that will correspond to a vector 1, 2, 0, 0. So that means x2 is free, and x1 is negative 2x2. So that means 1, negative 2 will be the corresponding vector. And when they say find a basis for the eigen space, you could put that in any order you want, right? So the basis for lambda equal 1 is that vector. The basis for lambda equal 5 would be this vector, and any combination of those will do. Those two will form the basis for those two eigenvectors. And I just wanted to tackle a 3 by 3 really quick and get that out of the way. And this way you'll have everything on the home. And again, if I take the determinant, oh, I'm sorry, not determinant. If I take a minus lambda I, wait, a minus, did I write determinant last time? Because normally I repeat myself. It's not determinant, it's a minus lambda I. Okay, there we go. So, if I take a minus lambda I, right, set it equal to 0, well, that would be what? 1 plus 2 is a 3, 0, negative 1, 1. Negative 3 plus 2 is a negative 1, and 4, negative 13, and 1 plus 2 is a 3, right? And if I row reduce this, I'll get 1, 0, negative 1/3, 0, 1, negative 1/3, and 0, 0, 0, which indicates x3 times, because x3 is free, 1, 1/3, and 1/3. Or simply 1, 1, 3. That will form the basis for the following corresponding eigenvector. And if I look at this problem, find the eigenvalues of the matrix. Do you remember what that theorem just said? Isn't this a triangular matrix? The eigenvalues are lambda equal a 4, lambda equal a 0, and lambda equal a negative 3. And that's what we're going to do in the next two sections. We're going to find the eigenvalues and eigenvectors given just a matrix. And our homework is right there, 1 through 17. Odd, page 275.